Good morning class. Today we are going to design Gantry Girder, a special steel element, and in some previous lecture during the class we refer that this gantry design types and the other structural components like a crane girder and the crane assembly which runs throughout the crane girder, and the crane girder runs through the gantry girder. So here I would like to discuss about the basic concepts about the gantry girder and how exactly it functions. So here you have to look that this one is the step up column, and this one is the channel section. You can see this one is the I section. So the entire section is a built up section. Here there is a top rail on which this wheel is run through, and this wheel is attached to the end of the crane girder, and on the crane girder there is one assembly. This one is the trolley plus crab plus motor, you can say that, and at the end the hook is hanged below it. This particular assembly has its own capacity to carry the load, and as per the shared material during the class you have one example. Just a minute. Yes, here we are. This one is the gantry girder problem is given to you. You can find this material in your Google Classroom. Design a gantry girder to be used in an industrial building carrying a manually operated overhead traveling crane for the following data. First of all, the data is crane capacity is 200 kilonewton. Here in this video, this 200 kilonewton capacity is the total weight that the crane can lift, which one is hanged below this hook. Self weight of the crane girder excluding trolley, this one is 200 kilonewton, excluding from the trolley weight. So the self weight of the crane girder, that means this one is your crane girder. We are going to design a gantry girder, not crane girder, but to design the gantry girder the weight of crane girder should be taken into the account. So this crane girder having a weight of 200 kilonewton, the total weight is 200 kilonewton, means this one is the capital W, not in the form of UDL. So whatever the weight of the crane girder is given to you, that you have to multiply with the span of crane girder. In this given data, self weight of trolley electric motor hook is given as a 40 kilonewton, means trolley plus electric motor plus hook, the total weight is 40 kilonewton. Means right now we are talking about this entire assembly. This one is a trolley plus the hook is hanged below it, and motor is attached to the assembly for the power transmission. Approximate minimum approach of the crane hook to the gantry girder is 1.2 meter. This particular hook and this particular trolley can travel through this crane girder from one end to the another end, but due to some circumstances as well as some several provision, whenever this hook is travel this side as well as the another side, then the approach is maximum far away 1.2 meter from this gantry girder. The wheelbase is given as 3.5 meter. That means this wheelbase means this one is your motor, crab and hook. This one actually lumped with the 40 kilonewton weight, and this one can travel here to there, but with the approach of 1.2 meter. But the wheelbase, that means the wheel here and the another wheel is here, and this clear distance between these two wheels is 3.5 meter. Distance between gantry rails is a 16 meter. So this one is the gantry rail at the top of the gantry girder. You can see clearly in this image also, this one is the rail section. It is very clearly mentioned here on which this wheel is on rest condition. So this one is your rail section. So rail section 1 is here, and in this entire drawing one rail section is here, and you can observe that another rail section is at the another side of the crane girder. So center distance between this rail section is given as a 16 meter, means this one is the span of crane girder, you can say that. Then center distance between columns, that one is given as a 8 meter. So you can see in this figure, both the crane girders are run through this gantry girder throughout, and this gantry girder is resting on the number of the columns. So the center column distance is given as 8 meter. So 8 meter is the span of gantry girder should be designed. Self weight of rail section is 300 Newton per meter on rest condition of the gantry girder. Diameter of crane wheels is a 150 mm. Steel is grade Fe 410. Design also field welded connection if required. The support bracket connection need not be designed. So for Fe 410 grade of steel, Fu is 410 MPa, and Fi, FIW, FIF, all this stuff having a yield strength 250 MPa. For hand operated OT crane, OT means overhead traveling crane, you can say that. So there are the two types of crane: mechanically operated overhead traveling crane known as a MOT, and electrically operated overhead traveling crane known as a EOT. The lateral load are considered always as a 5% of maximum static wheel load, and the longitudinal loads are considered as 5% of the weight of the crab lifted. So longitudinal load is 5% of the weight of crab and weight of lifted object, you can say. Longitudinal load means, this one is one of the image, when this particular crane travels on the crane girder and when it suddenly breaks, then in this direction you can say that it's a surge. That one is the lateral load on this gantry girder. When these crane girder are traveling from here to here in this direction, and when it suddenly breaks, then that one is the braking load. The braking load are always in the longitudinal axis of the gantry girder, so that's why this load is known as a longitudinal load. And when the crane is traveled through the crane girder from here to there, means particular in this special direction, then it will create a lateral load. This one is known as a surge applied directly on the gantry girder. So gantry girder subjected three loads. First one is the wheel load, which one is known as a transverse load acting in a downward direction. Surge load means you can say a lateral load always acting in a lateral direction of the gantry girder. And third one is the braking load, which one is parallel to the gantry girder, so along the axis, so you can say that it's a longitudinal force. So this particular special element should be designed with the combination of three directional forces: transverse, longitudinal, this one is a lateral and longitudinal force. So these are the percentage directly acting in terms of lateral and longitudinal loads due to the performance of the crane. Maximum permissible deflections limits are given here. First of all, we have to refer that the coded provision in which all this criterion is given. This one is the IS 875 part 2. On this code, especially you can say that it's a table 2 and this one is the 6.1 close and this one is the table 3, and at the lower side of the table 3 you can find the type of load. This one are the vertical loads for the electric overhead crane. So this particular condition should be considered as per in situ condition of your gantry girder. First of all, given as a 25% of maximum static loads for the crane girders for all cases of crane, 25% of the column supporting class 3 and 4 crane, 10% for the column supporting class 1 and class 2 crane, and no additional load for design of foundations. When vertical loads for hand operated cranes, then 10% of the maximum wheel load for the crane girder only. So in this case, in our example, it is clearly given that this crane is a manually operated overhead traveling crane. So that's why, as per that the code of provision, we have to consider the vertical loads for the hand operated crane is a 10% of the maximum wheel loads for the crane girder only. Horizontal forces transverse to rails. So the first one is for electric overhead cranes with the trolley having a rigid mast for the suspension of the lifted weight such as a soaker crane, stripper crane, etc. This one is considered as a 10%. And for all other electric overhead crane and hand operated cranes, it's always considered as a 5% of the weight of crab and the weight lifted by the cranes. Means the crane capacity and the trolley plus crab plus hook weight, the total weight, and only 5% of that the total weight is considered as the horizontal forces transverse to rails. And third one, horizontal transaction forces along the rails for overhead cranes, either electrically operated or hand operated. So for the longitudinal force, you can say it's along the rails, means this force are a longitudinal force, which are considered as a 5% of all static wheel loads. Alright. So that's why we consider here and that both the cases they are for the 5% and 5% of the maximum static wheel load. The maximum permissible deflection is considered as L by 500 for MOT. For EOT less than 500 kN capacity is L by 750. For EOT greater than 500 kN capacity, it's L by 1000. And other moving loads such as charging cars, etc. L is the span of gantry girder. For all these cases, for the charging cars, it's L by 600. Partial safety factors, you already aware about that. Gamma M0 1.1 and gamma MW 1.5 for the side weld and 1.25 for the shock weld. So here our problem begins. First of all, look at the sketch of the gantry girder functionality. This one is the trolley or crab and hook is hanged through that the trolley and the weight is lifted through that the particular hook. So this total self weight of this trolley, motor, etc. plus hook plus the weight lifted beyond the hook all are working as a concentrated force on this crane girder. All are working as a concentrated force on this crane girder. Right now we have to design this gantry girder. A section is I and the channel section lying on the top flange of the I section. This one is one of the built up section. Right now, which one is designed as a gantry girder? We are going to design a gantry girder, so we have to consider the maximum possibility of the forces on the gantry girder, and for that maximum possibility of the forces we have to analyze that particular gantry girder, and then we have to design this particular section. Now the maximum hook approach towards the gantry girder is given as a 1.2 meter, and the center distance between two rails is given as a 16 meter in our example. So this crane girder is acting as a simply supported beam as given here in your notes. This 16 meter is the distance between two rails, means between two gantry girders. This one is the span of crane girder. This particular trolley, crab, hook and the maximum capacity are traveling through this distance to this one, and the maximum possibility to transfer the force on the crane girder, gantry girder, then you have to move your assembly maximum towards the gantry girder. So that's why we applied this weight as consideration of the maximum considered load on the crane. Means 200 is the crane capacity plus 40 is the self weight of the your trolley, crab, motor and hook. So the total weight is 240 and it is acting as a concentrated force on the crane girder. When we are multiplying with this total force with the factor of safety, it's a load factor, then you will have the concentrated force 360 kilonewton acting at a 1.2 meter distance apart from gantry girder. Now the self weight of the crane is given as 200 kilonewton. The span of the crane girder is given as a 16 meter. So to convert into the uniformly distributed load, the total load divided by span is equal to 12.5 kilonewton per meter. This one is the self weight of the crane girder. So factor UDL is 1.5 into 12.5. Your answer is 18.75 kilonewton per meter. So here is your problem. The self weight throughout the span is 18.75 kilonewton per meter, and the point load acting at a 1.2 meter distance is a 360 kilonewton. Now we have to find out what are the support reaction here as well as here. So the maximum load you will get here as your maximum load is towards the support A. So the support into total distance is equal to 360 into 16 minus 1.2 plus 18.75 into 16 square divided by 2. So for this trial I just consider the moment about support B is equal to 0. Then I will get your reaction at support A is equal to 483 kilonewton and RB as a 177 kilonewton. So the reaction from the crane girder is distributed equally on the two wheels at the end of the crane girder. So here, as per this given example, you can observe that at the end there are two wheels, but the crane girder is a single element. So the maximum support reaction is here as 483 kilonewton, and through this section at the equal distance of these two wheels, on each wheel it is distributed like 483 divided by 2. So it's a W by 2 is equal to 241.5 kilonewton. 483 divided by 2 is equal to 241.5 kilo Newton. Now consider your problem as this data given in a form of that the center distance between columns, it's a 8 meter. As I told you earlier, center distance between these two columns is 8 meters. So this one is your span of gantry girder. Here the major challenge is you are facing a problem of the gantry girder having a span of 8 meter supported by two consecutive columns, on which the forces acting are first the self weight of the gantry girder plus self weight of the rail. As well, two wheels are moving from one end to the another end of the gantry girder. So, to justify the point of maximum bending moment, you have to follow the method of influence line diagram. And with the help of influence line diagram, you will get the solution such likewise the point of maximum bending moment should be achieved only if you will just keep your wheels at the distance of 3.5 meter with the wheelbase at particular distance at a 1/4 cg of wheel load and the cg of gantry girder must be coincide. Means here I am going to represent this actual scenario to put your particular wheel load on the gantry girder, so you will get the maximum bending moment point. So that's why we require some shapes. Alright, here this one is an element, you can say it's just let me press key shift. Okay, fine. This one is your beam element. Let me color it as a black so you can see it very clearly. This one is your support, but the arrow is little bit downside, so the support can be traveled from here to here as you know. Just a minute. Okay, the another arrow we are going to put here as a support reaction. Alright, so this one is your gantry girder and these two are consecutive columns at the distance of 8 meter. Now consider this line representing just a minute. So once again we have to draw this line, as we can say it's representing the center line of the gantry girder. And let's color it black. So Fine. So you can say it's a mid span of your gantry girder, and there is one assembly. You can say that C. Alright, these are the two wheels, and the center distance between two wheels are given as a 3.5 meter. Given as a 3.5 meter. Alright, so this one is the 3.5 meter distance, and you have to draw the center line passing through this assembly. Alright, lead color is as a black, so we have very clear depicts here. So this one is center line of this wheel load, and once again you have to create, this one is the half span of this wheelbase, and once you will create another half of the half span. So okay, so you can say this distance is not 1 point, it's a 1/4 of this wheelbase, because it's a L by 2, it's also L by 2, and it's a L by 4, so it's a 1/4 of the wheelbase. And when you just transfer this entire assembly and just coincide these two lines together, means this 1/4 point mark line and the CG line of this gantry girder and 1/4 line of this wheelbase are coincide together, then one wheel at the distance of 1/4 into 3.5 meter as per the given data. Total clear distance is 3.5. It is wheelbase given in the data. So the half is 1.75, 1.75, and from the CG it's a 1.75 divided by 2. So that's why it's a 0.875 meter. So as per this particular drawing, you can say that whenever you are going to keep your wheel load in this particular position, then and then you will find the possibility of the maximum bending moment at this wheel base. This one is the location, please mark, this one is the location to achieve the maximum bending moment. This one is the location of to achieving the maximum bending moment. Alright, this one is the point under this wheel load, which one is very near to the CG of the gantry girder as per this particular calculation. So here we are going to find out the maximum bending moment experienced by the gantry girder. So that's why we arrange this two wheel load such a likewise that from that the 8 meter, this one is the center point of the gantry girder. As per the scale it is not clear, but you can say that yes, it's a center, and this wheel is kept at the distance of 0.875 meter, is a 143.5 meter. Alright, so it's a 0.875 meter. This wheel is kept as this particular CG of this gantry girder point. You will find the maximum bending moment here. So these wheel loads are 241.5 kN, 241.5 kN as W by 2. We achieved that. The self weight of this gantry girder is assumed as 2 kN, and the self weight of rail is given as a 300 Newton per meter. So it's a 0.3 kN per meter. So the total self weight is 2 plus 0.3 is equal to 2.3 kN per meter. So the factor UDL is 2.3 into 1.5, it's a 3.45 kN per meter. So the position of one wheel load from the midpoint of the span. So wheel base divided by 4, as I told you earlier, 3.5 by 4, it's a 0.875 meter from the CG of the gantry girder. Bending moment due to live load only. Here please mention bending moment due to live load only. So while solving this problem, you don't have to consider this UDL into the account. You have to solve out the gantry girder having only two wheel load acting on it, means 241.5 and 241.5 at this particular distance mentioned here. No UDL you have to consider into the account. Why? I will tell you later as we are go through this particular design. Taking moment about D. So this one is the support C and this one is the support D. Alright. So taking the moment about D. So once you have taken the moment about D, then at this point moment is equal to 0 as a simply supported. So RC into 8 first of all. So it's a RC into 8 is equal to 241.5 into this distance from this support to this one, and this one is 4 minus 0.875, so it's a 3.125. So yes, here it is 241.5 into 3.125, and this load into this distance from this support D to the second wheel load. So it's a 241.5 into 8 minus 1.375. It is given as, so the reaction at the support means the column is a 294.33 kilonewton. Taking moment about C, then you will get the reaction at a D point. Same procedure you have to follow as per the above one. So RD you will get as a 188.67 kilonewton. Maximum bending moment due to live load. Now, maximum bending moment due to live load. So here 188.67 kilonewton is the reaction at support D. And maximum bending moment due to live load, it's a 188.67 into 3.125. So you can say that. So this one is the reaction here, and maximum bending moment you will find here at this point below this wheel load. So this one is the point at which you will get the maximum bending moment. So that's why simply RD into this distance, that's a 3.125. It's a maximum bending moment experienced by the live load. So it's a 589.6 kilonewton into meter. Now I told you that you don't have to consider the UDL right now, because we have to consider the bending moment due to impact. So we have to consider the impact bending moment, and that should be a 10% due to live load, as we discussed earlier. As per that, the code of provision for these vertical loads for hand operated cranes, 10% of maximum wheel load for crane girder only, and this one is the impact. Alright, this entire clause 6 is for the impact effect, loading effects due to impact and vibration. So for this vertical load for hand operated cranes, 10% of maximum wheel load for crane girder only, maximum wheel load. So we have to consider only wheel load, not UDL. So that's why we didn't calculated this UDL in a account while calculating the maximum bending moment. Alright, so whatever the bending moment we achieved through this, the transverse load of the wheel, 10% of this bending moment is considered as due to impact. So 0.10 into 589.6, so it's a 58.96 kN into meter. The total due to live and impact loads, so 589.6 plus 58.96, so it's a 648.56. So this one is the bending moment due to wheel as well as impact, but both are live load. But bending moment due to dead load means the self weight of gantry girder and rail section, it's a WL square by 8 is equal to 3.45 into 8 square divided by 8 is equal to 27.6 kN into meter. So this bending moment is also should be added in this total amount. So 648.56 plus 27.6 is equal to 676.16 kN into meter. Now to find out the maximum shear force. So to find out the maximum shear force, you have to consider one wheel exactly above the column. So you will get a maximum reaction on this column, and maximum reaction is always considered as a maximum shear force in your given problem. So one wheel is here and second one wheel is a 3.5 meter apart from the first wheel. So another load you have to keep at a 3.5 meter as a 241.5 kilonewton. The entire element is subjected to UDL as a dead load 3.45 kg per meter, and your span of the gantry girder is a 8 meter. So now taking the moment at D, RC into 8 is equal to 241.5 into 8 plus 241.5 into 4.5. So you will get the value of RC, and this RC is the maximum shear force experienced by the your gantry girder. But this shear force always considering the lateral force plus transverse to the rails. So that's why it's a 5% of the weight of crab and weight lifted. So 0.05 into 240 is equal to 12 kilonewton. So factor load is equal to 12 into 1.5, it's a 18 kilonewton. So it's a 360. You can directly consider 360 here, or rather you can consider the service load and then after you can factor it. Both the method is correct. Lateral force on each wheel is equal to 18 divided by 2 is equal to 9 kilonewton. So when your crane is traveling throughout this, then this one will create the maximum shear force. Lateral force transverse to the rails should be calculated as 5% of the weight of crab and weight of lifted, and that we calculate as a 9 kilonewton. So the maximum horizontal reaction due to the lateral force by proportion at C, maximum horizontal reaction due to lateral force by proportion at C. So lateral force into reaction at C due to vertical load divided by maximum wheel load due to vertical load. So 9 into 294.33. 294.33 is the RC that you obtain. Divided by 241.5. 241.5 is your wheel load. So this one is the ratio. 9 is the force due to the lateral effect of the wheel load, and this one is the transverse wheel load. So the lateral to the transverse ratio should be multiplied with that the particular proportion with respect to the reaction at a C, and you obtain the value as a 10.97 kilonewton. So horizontal reaction due to lateral force, D is equal to 18 minus 10.97 is equal to 7.03 kilonewton. So it's a reaction at D. So this is the total load. One wheel load is 9. So two wheel load is equal to 18 minus 10.97 is the one of the reaction at C. So the reaction D is equal to total load minus reaction at C. So you will get the value of 7.03 kilonewton as a reaction at support D. Now maximum bending moment due to the lateral load by proportion. So 9.0 divided by 241.5 is the proportion lateral to the transverse. Multiply with the bending moment due to live load only is equal to 21.97 kilonewton into meter. Maximum shear force due to the lateral load by proportion. So it's a ratio of the lateral load of wheel divided by transverse load of wheel and multiply with the maximum shear force that we obtain here. RC is equal to 377.34, and you will get the maximum shear force due to the lateral load by proportion. It's a 14.06 kilonewton. So for the primary trial section, to fulfill all this bending moment and shear force as well for the lateral, longitudinal and the transverse design, the approximate depth of this section is L by 12. This one is the trial selection. So L is your span of gantry girder is 8 meter, so 8 into 10 to 3 mm divided by 12. So it's a 666.66 mm. Nearby you can consider as a 600 mm. Approximate width of flange L by 30. It's a 8 into 10 to 3 divided by 30. It's a 266.66 mm. So you can consider as a 300 mm. These are the trial sections consideration you have to keep in your mind while selecting the section. Approximate section modulus required. Now ZPZ is equal to 1.4 mz divided by Fy. This 1.4 is that the shape factor for that the ideal I section, and for you built up section you can also consider it 1.4 into 6.16 into 10 to 6 divided by 250. So this one is 3786.5 into 10 to 3 mm cube. This one is the maximum bending moment, combination of the bending moment due to live load, bending moment due to impact and bending moment due to dead load. Let us try ISWB 600. ISWB 600 at 1311.6 Newton per meter, which ISMC 300 at 351.2 Newton per meter on its top flange as shown in model. The relevant properties of the sections from appendix in book. So these are the property as you consider the two section ISWB 600 and ISMC 300. Alright. So both these sections can build a new section as per the shown here in the figure. This one is the I section, and above the flange, top flange of the I section, there is one channel section on a resting condition, and this entire lookwise a T known as a built up section and should be designed as a gantry girder for that the considering the given problem. So property like a thickness of flange for the ISW 600 as well as the channel section, all these stuffs are given here. But you have to just focus here. IZ and IY means as per your data given in the steel table, it's always IX and in the form of IY. So here IX of this I section and IX of the channel section are not more as the IX of that particular section. Let me explain. This I section is look like as given in the steel table. You can also refer the steel table here. Now we have to go to the I section. So yes, these are the I section. Let me find out the IS. Oh, we go to the channel right now. JC is a B. So it's a B, so that's why I think it's the ISHB. Where are the ISWB 600 sections? Yes, here no, it's IS and B. Where is ISWB 600? Sorry. Yes, it's ISWB 600 and we consider 1337. This one is our section. Alright, and as per that the given data here IXS IYY is given to you all, and as per this given data let us match. Yes, it's same as per that the steel table, right? 106.198.5, and in our given data we also consider 106.198.5. 106.198.5 into 10 to 4 mm raised to 4, and IYY is given as 4702.5. So it is also given as a 4702.5 into 10 to 4 mm3. Now look at the channel section. Channel section is the section ISMC 300. So let us check the moment of inertia of this given section. ISMC 300. So these are the channel section you can see here. ISMC 300. Yes, here it is ISMC 300. Alright, and for this section, okay, IXX as well as IYY. So IXX is given as 6362.6. yes, it is, and IYY 310.8 something. So yes, it's a 310.8 into 10 to 4. Height is given, R1 is given, and CYY means the CG is given here. You can also refer the CG in this figure, it is clearly mentioned here. This one is your CG, this one is the CG point is located here, and CYY is the distance given from the CG axis to the most outer side axis of the flange of the channel, sorry, web of the channel. Moment of inertia of the gantry girder, the distance of NA of the built-up section from the extreme fiber of compression flange. So the moment of inertia gantry girder, the distance of NA of built-up section from the extreme fiber of compression flange. So the Y bar is equal to sigma AY divided by sigma A. Here is the area of the I section, area of the channel section. This one is the total height from the bottom. So you have to consider first of all this image to calculate it. So it's a 7.6, and from here to here it's a 300. So that's why it is considered as 300 plus 7.6. From the top, 2564 into 23.6. 23.6 is also from the top. Let me show you. The CG is given here, and from the top the distance of the CG of the channel section is given in the data as a 23.6 mm. You can also refer it here. From this extreme edge of the wave of the channel section to the CG distance is CYY 23.6 is given in the data. So this one will help you to find out the Y bar. It's a 247.59 mm. So 247.59 from the top, you already identified this distance. Now, gross moment of inertia of built-up section IZ gross is equal to IZ beam plus IZ channel. The channel is placed over the I section in such a manner that its YY axis becomes ZZ axis. Therefore, in calculating IZ of the total section, IY of the channel will become IZ of the channel. Let me explain. Here in the steel table, the channel section orientation is likewise this. So this one is the YY and this one is the XX, and as per our example, this one is the ZZ. So this one is the ZZ, this vertical is the YY, but in this our built-up section, your section is as per this resting condition. So this axis become the XX and the vertical axis become passing through the I as well as channel section is become as a YY. So the inertia about this axis will become IXX and inertia about this axis will become IZZ, IYY. So please consider this. Don't do mistakes while solving this example. IZ gross is equal to 106,198.5 into 10 raised to 4. It's IXX of the beam's I section plus A into Y bar square. So that's why the area of I section into Y bar square means 247.5. So it's 247.59. You can see in this figure from the bottom it's a 307.6. As you know that the total depth of this section is the 307, and the depth of this new axis is 247.59. it's a CG because about this axis it's always lying in same condition, but about this one it's lying from the top as a 247.59 mm distance. So the 310.8 into 10 raised to 4, it's a inertia of the channel section plus A area into Y bar square, it's a 247.59 minus 23.6. Here is one, this condition is don't consider this 307.6 as this arrow. 307.6 is from the top to here. Here is the CG of the I section from the top, and the total distance is 300 plus 7.6. 7.6 is the wave thickness of the channel section. So from the top extreme fiber to the CG of the I section distance is 307.6, and the depth of this CG of the entire section means you can see it's a central axis, it's a 247.59. So as per the gross inertia equation, it's a inertia about the axis plus A into y bar square. So here y bar is CG to neutral axis distance. So CG to neutral axis distance is 307.6 minus 247.59 is this one, and this one is mentioned here. For this channel section, the neutral axis to the CG of the channel section, CG of the channel section is at the distance 23.6 from the topmost fiber, so it will locate here. So the distance from here to here is considered as 247.59 minus 23.6. so that's why this one is considered as the inertia of channel section plus A into y bar. A is 4564, but y bar is 247.59 minus 23.6 square. So this one is the IZ gross. IY gross is nothing, just IY of beam plus IZ of channel as per the data, and as per that the built up section it's a IY itself. So it's a 4702.5 into 10 raised to 4 plus 6362.6 into 10 raised to 4. So the IY is given as here. If you get the solution of this one, then you will get the IZ value is 135,543 into 10 raised to 4, and Z is equal to IZ divided by Y, and your Y is 600 plus 7.6 minus 247.59 from the bottom is equal to 3764.98 into 10 raised to 3 mm cube is your elastic section modulus. Now for plastic modulus section, we have to ignore the fillets. Equal area axis theorem that should be adopted. Equal area axis will directly help you to find out the location of plastic axis, and through that you can calculate the plastic modulus of the section. So to find out the plastic axis, the equal area axis theorem should be adopted. So you have to consider the whatever the area apart from that the axis above the section and below this axis, both the area should be same. So that's why we assume that axis must be appear at some distance here. You can say that. So as per this figure, the bottom side the total area. This one is the non-figure 21.3 into the width of flange is you can say that it's a 250 into 21.3 plus this one. So the entire depth of wave should be divided into the two parts. The above side portion is known as a y1 bar, and the below side of this extreme depth portion is known as 600, the total depth of the I section, minus 2 times 21.3. So that one is a small d, and small d minus y1 bar. So this one is mentioned as a here. The total depth of the I section is 600 minus 2 times the thickness of flange 21.3. So this one is considered as the effective depth of the wave, means a small d, and small d is mentioned likewise that, and minus y1 bar because we assume that our neutral axis is lies at some distance here. So this distance, because this above side this distance from this edge to here, there is one imaginary axis. Imaginary axis is passing through like it here, and this one is your plastic neutral axis. So above side, the total area is always equal to the below side area, and you have to identify this bottom mark depth. So that's why you consider this one as a top distance as a y bar. So the bottom one is a d minus y1 bar, and d is a 600 minus 2 times 21.3 minus y1 bar into the thickness of the web, and thickness of the web is given in the data is a 11.2. And the above side the area, the entire area of the channel section is 4564 plus 250 into 21.3 means the top flange area of the I section plus y1 bar into 11.2. So while equating this equation, this logic, you will get the y1 bar is equal to 74.95 mm, and this one is distance from here to something at here, and this distance is 74.95. So your plastic axis is located at here through the section parallel to x-axis. Your plastic axis here. This distance is 74.95 mm from the lower surface of the top flange of I section, as we can say. Plastic section modulus of the section above equal area axis. So that's why right now you have the location of axis. So this ZP-Z1 is equal to 300 into 7.6. 300 is the total depth of your channel section. You can say that it's a span of web, multiplied by 7.6 is the thickness of web, into 74.95 plus 21.3 plus 7.6 divided by 2 means the entire this section having the CG here at its center. So the center to this distance of the plastic neutral axis. So you can say this one is the center, which means located here, and from the center the distance of the plastic neutral axis. So this one is 74.65, this one is 21.3, and this one is the 7.6 divided by 2. So this one is the distance, this one is the area of web, plus 2 times 90 minus 7.6, because this distance is given as a 90 from here to here. This one is the flange of channel section, this one is 90. We already consider this entire area 300 by 7.6, so we have to consider the flange's depth as a 90 minus 7.6. So it's 90 minus 7.6, and the thickness of these flanges, is given as a 13.6 as per steel table. So 2 times 90 minus 7.6 into 13.6 is the area of the flange, as this one is located at here as well as here at both the sides. Into, now you have to identify the distance from the plastic neutral axis to the CG of your flange. So 74.95 plus 21.3 minus 90 minus 7.6 divided by 2 plus 250 into 21.3. Here you have to consider this flange, the top flange. It's a 250 into 21.3 is the thickness of flange, into the distance of CG. CG means 21.3 divided by 2 plus 74.95. So the total distance is 74.95 plus 21.3 plus divided by 2 plus now this portion. So this one is the depth is a 74.95 and the thickness is 11.2. So So you have to consider as 74.95 into 11.2 is the area, and the distance of this area CG to the plastic axis is a 74.95 divided by 2. So your total answer is 838.775 into 10 raised to 3 mm cube. So plastic section modulus of this section below equal area axis. So the below side, the plastic section modulus, you have to consider likewise 250 into 21.3. So this one is the section modulus considered for that the bottom flange of the I section. 21.3 into 250 is the area, and CG2 distance is, you can consider the total this distance is 600 minus 2 times 21.3 minus 74.96 or 95, this one, plus 21.3 divided by 2. So you can consider is 250 divided by 20 is the area, and the distance is 600 minus 21.3. It's from the top, minus 74.95 minus 21.3 divided by 2. So it's a distance from here CG of this flange to the plastic neutral axis located at a here, plus from this plastic neutral axis to this wave, and this wave CG is located here. So the CG located here at the center, and you have to consider the distance from here to there. So this one can be obtained through 600 minus 2 times 21.3 minus 74.95 square into 11.2 divided by 2. So ZPZ2 you will get as a 3929.202 into 10 raised to 3 mm cube. So the total plastic section modulus is equal to ZPZ1 plus ZPZ2. So the section plastic modulus is a 4767.977 into 10 raised to 3 mm cube. Plastic section modulus of compression flange about YY axis. So ZPFY is equal to, right now you don't have to identify the distance from that the CG as it is symmetric about the YY axis. So simply 250 into 21.3 into 250 divided by 4 plus 2 times 300 minus 13.6 into 2 square into 7.6 divided by 8 plus 2 times 13.6 into 90 into 300 minus 13.6 divided by 2. Your answer is 824.763 into 10 raised to 3 mm cube. The plastic section modulus of compression flange about YY axis. Here the plastic section modulus of compression flange about YY axis. Why we consider here only for the compression flange about YY axis? Because you have to observe here in this PPT shared with you, whenever the lateral load is applied in this particular direction, as we already considered, if the lateral load is applied in this particular direction region, due to this movement of the crane from here to there, when it suddenly breaks, then the force should be transmitted in this direction as per the shown arrow, and that should be applied here. But in that the lateral direction, you can see that the top compression flange is only in the rest condition with respect to as a support to this column. The bottom side portion is not laterally supported, only in contact here the top compression flange. So the top compression flange only play a role to resist the lateral force applied through that the movement of this trolley. So that's why we only consider here the top flange of the I section, the wave of the channel section, and the two flanges of the channel section are considered as a top flange of the built up section, the entirely, and The section modulus should be calculated for that the top compression flange of the built-up section only. Now the classification of the section. Outstand B is equal to BF by 2, 250 divided by 2 is a 125 mm. B by TF is a 125 divided by 21.3 is equal to 5.86 less than 8.4 epsilon. Outstand channel B is equal to BF minus TW 90 minus 7.6 is 82.4 mm. So B by TF is 82.4 divided by 13.6 is equal to 6.05 less than 8.4 epsilon. D by TW of the wave I is equal to H by H minus 2 times thickness of flange divided by TW. So H minus 2 times thickness is a small d. So your answer is 49.76 less than 84 epsilon. Hence entire section is plastic as per the table 2 classification of section as per the Indian standard 800. Check for moment capacity. Local moment capacity. The local moment capacity as per the IS 800, you are very well familiar about that. You have to quickly go through the section 8. Oh, it's too old, so it's 1984. As per the code of provision, that bending moment design equation that you already familiar about, it's a beta b ZPZ Fi divided by gamma MO, which one is less than equal to 1.2 ZE Fi divided by gamma MO. Here plastic section of beta b is equal to 1, ZPZ that you calculated into 10 raised to 3 mm cube, Fi 250, gamma MO 1.1. So your total bending moment about Z axis is 1083.63 kilonewton into meter, which one must be less than equal to 1.2 into 3764.98 into 10 raised to 3 into 250 divided by 1.1 into 10 raised to minus 6, which one is 1026.81 kilonewton. So here your 1.2 ZE Fi divided by gamma MO is 1026.81 kilonewton. So that's why MDZ should be considered as 1026.81 kilonewton, which one is greater than 676.16 kilonewton. The trial section seems to be safe by sufficient margin in the moment capacity and can be checked for combination of loads as laterally unsupported beam. So that's why MDYF, so load in a lateral direction as shown earlier, this one is the lateral load due to the movement of the crab, and which one is applied on that the gantry girder. So that's why we already calculated the analytical bending moment. Right now we have to calculate the bending capacity about the y-axis of the gantry girder in a lateral direction. So beta b is ZP YF into Fi divided by gamma MO. Why the F is mentioned here? Because the top compression flange plastic section was only considered for that the y-axis. Less than equal to 1.2 ZE Fy into Fi divided by gamma MO. So 1.0 is a beta b as it's a plastic. ZPYF is already calculated 824.763 into 10 to 3. Fy 250 1.1 into 10⁻⁶. Your answer is 187.44. Less than equal to 1.2 into 580.92 into 10⁻³ into 250 divided by 1.1. Your answer is 158.43 km. So lateral bending moment resisting capacity of your gantry girder is not this, it is 158.43 km. And which one is greater than the lateral bending moment experienced by your gantry girder? And that you already calculated as, in this lateral direction, the bending moment you calculated in the previous step, and this one is here. Bending moment due to the lateral load by propulsion is 21.97 kN. So your capacity is far greater than the analytical moment, as it is 158.43, right? So the combined check for the local moment capacity is mz divided by mdz plus myf divided by mdyf is less than equal to 1.0. This combination is given in the Indian standard in a form of n divided by nf plus mz divided by mdz plus myf divided by mdy less than equal to 1.0, but no axial force is considered here. So that's why the combination of the transverse moment and the lateral moment is considered as a unity equation. So 676.16 is the maximum analytical bending moment. The maximum transverse bending moment capacity is 1026.81. The maximum lateral bending moment is 21.97 analytical, and the design one is a 158.43, and the ratio is 0.797 is less than 1.0. So your section for the combination of the transverse and lateral bending moment is safe. Now check for the buckling resistance in bending. The elastic lateral torsional buckling moment MCR is given as per the Indian standard, in especially the clause number 9.2. It's given as C1 pi square EIYF HF 2L square LRD 1 plus 1 by 20 LLT by RY divided by HF by TF raised to 2 and whole bracket raised to 0.5. HF is equal to H equal to 600 plus 7.6 is equal to 607.6 mm. Effective length LLD is 8 into 10⁻³ mm, as it's the length of gantry girder. Thickness of flange is a 21.3 plus 7.6 is a 28.9 mm. Radius of gyration is calculated as a Ry is equal to under root Iy by A. Iy is given here, and divided by A. A is the area of I section plus channel section. So your Ry is 71.57 mm. The coefficient C1 is 1.046 is selected as per the annexure C. MCR is equal to 1.046 into pi square into 2 into 10⁵ into 11065.1 into 10⁴ into 607.6. Just me look into here, the annexures are provided as per the consideration or not. So we can directly take the value into the account as per our assumption. It's a previous code, so that's why I can't find anything as per the new code, but I will over about as all the things previously mentioned in the design of beam as well as the plate girder, so you can find out it very easily. As well, I will also share this code of provisions separately within your Google Classroom, so you can directly take the advantage of this given period. So please everyone focus here. These are the deflection limits as we discussed earlier. which are given on the page number 35 of the IS 800-1984. So MCR is obtained as of 1684.72 into 10 to 6. Non-dimensional standardness ratio is lambda LTZ under root beta B ZPZ Fy divided by MCR. So it obtained as a 0.842. Alpha phi LTZ is equal to 0.5 in bracket 1 plus alpha LT lambda LTZ minus 0.2 plus lambda square LTZ. So alpha LT is 0.21 is the imperfection factor, you can say that, and phi LTZ is equal to 0.5 into 1 plus 0.21 into 0.842 minus 0.2 plus 0.842 square is equal to 0.921. Xi LTZ as per the given equation, it is obtained as 0.7726. Design bending compressive stress FBD is equal to Xi LTZ Fy divided by gamma M0. It's a 175.59 Newton per mm square. So design bending strength MDZ is equal to beta B ZPZ into FBD. So your design bending strength is 837.20 kN, which means greater than 676.16 kN. So you can say that with application of this magnitude of bending moment, your section will go under the lateral torsional buckling. But this one is greater than 676.16 kN as it's our factor bending moment, analytical one. So that's why our section is safe against the lateral torsional buckling. The gantry girder is safe in the bending under vertical loads. Since the lateral force are also acting, the beam must be checked for the biaxial bending. The bending strength about the y-axis will be provided by the top flange only as the lateral loads are applied there. So MDY is equal to ZYT into Fy divided by gamma MO, and it is obtained as ZYT is obtained as about y-axis for the top flange only. It's a 580.92 into 10 to 3 mm cube. Assuming the moment of inertia of the top flange to be half of the moment of inertia of I section, MDY is equal to 580.92 into 10 to 3 into 250 divided by 1.1 into 10 to minus 6 is equal to 132.02 kN/meter. MZ divided by MDZ plus MY divided by MDY less than equal to 1.0. So this one is the capacity. This one is also considered as the lateral capacity of the section. So that's why the factor is considered as a 0.974 less than 1.0. It's always safe. Check for shearing capacity. Maximum shear force due to wheel is equal to 377.34 kN as RCB obtained earlier. Impact load is 10% of the shear force, so that's why 0.1 377.34 is a 37.73 kN. Design shear force is 377.34 plus 37.73. It's a 415.07 kN. Shear capacity is equal to AV into FIW divided by under root 3 into gamma MO. AV is the area of wave, 600 into 11.2. FIW is 250 under root 3 into 1.10. So shear capacity is 881.77 kN, which means greater than 415.07 kN. So it's safe. Maximum shear is 415.07 kN, which one is less than 529 kN. 0.6 VD. So it's a case of lower shear, so no reduction will be therefore there in the moment capacity, as we discussed it earlier. If your V is greater than 0.6 VD, then it's a case of higher shear and you have to calculate the reduced bending moment for that. but here is the case of lower shear, so you have to just follow the equation MD is equal to beta B ZPZ Fy divided by gamma MO that we already did, and it is safe, so no need to be worried. Web buckling check. Web should be checked for buckling under the wheel load. Buckling resistance is equal to B1 plus N1 into TW into FCD, where B1 is assumed as 150 mm, is a stiff bearing length. N1 is equal to 600 divided by 2, means the half of the I section in terms of depth plus 2 times thickness of the web of the channel section, so it's a 315.2 mm. Lambda W is equal to 2.45 divided by TW is equal to 2.45 into D1 600 minus 2 times 21.3 plus 17 is the root radius, divided by 11.2 is equal to 114.49. Lambda W is equal to 114.49 Fy 250 MPa, so that's why from the table FCD is equal to 89.64 MPa. Buckling resistance 150 plus 315.2, it's a N1 into 7.6 is a your equational TW into 89.64 into 10 raised to minus 3. 89.64 is Fy, but here is the case of FCD, so that's why Fy is replaced with the FCD. So it's a 316.9 kN, which means greater than 241.5 kN is a static wheel load, so which is safe. Deflection check. Delta is equal to WL cube into 3A divided by 4L minus A cube divided by L cube divided by 6EI. This equation is derived as per the condition of the loading of the gantry girder due to influence line diagram of the two wheel load when applied on the single span to achieve the maximum bending moment. So as per this diagram, at which point we will get the maximum deflection? At the point when we will find the maximum bending moment, and for this, at this point, to find out the maximum deflection, the equation is derived in the terms of delta is equal to WL cube into 3A divided by 4L minus A cube divided by L cube divided by 6EI, where W is equal to maximum static wheel load, it's a 161 kilonewton unfactored. A is equal to L minus C divided by 2, it's a 8 into 10 raised to 3 minus 3.5 into 10 raised to 3 divided by 2, it's a 2.25 into 10 raised to 3. Vertical deflection is equal to 161 into 10 raised to 3 into 8 into 10 raised to 3 cube into, as per this equation, when you put all the parameters, you will get the deflection 9.56 mm. Permissible maximum deflection is L by 500, 8000 by 500 is a 16 mm. So permissible is greater than actual one. So that's why for the deflection, the design is safe. Now design of connection. Required shear capacity of weld. Q is equal to VA Y bar divided by IZ. V is the shear force. A is the area of channel section. Y bar is a 247.59 minus 7.6 at the distance from the central axis of the built up section 239.9 mm. IZ is equal to 135543 into 10 raised to 4 mm cube, that we already achieved. Q is equal to 304.82 Newton per mm. This one is the applied shear at in between the channel as well as the top flange of the I section. Let's check the shear strength provided by the weld. So let's provide 3 mm weld size to connect the channel with the flange. Strength of welded provided is a 0.7, it's a K into the 3 is a S, means the weld size. 410 is a FU divided by under 3 into 1.5. 1.5 is the gamma ML at its you can consider it's a site welding. So that's why 331.39 Newton per mm. And which one is greater than this? Applied shear per mm. So that's why the welding design is okay. So here the design of the gantry girder for the applied load is already completed, but there is one more load for which we have to also check for the design of the gantry girder, and that one is the fatigue, because number of cyclic repetition loading of the crane means when the crane travel through the gantry girder, then enormous points fill the load, and once the wheel is passed through, then it's a removing of the applied loading. So that's why at that the time the loading and unloading application on that the gantry girder will create a fatigue as the given data of that the said problem. Let me discuss. Check the same for the fatigue strength for the following data. The crane operates for 225 days per year. The working hours 9 am to 5 pm. Maximum number of trips per hour is 3. Design life is a 50 year. So please refer it very carefully, everyone. The crane operates for 225 days per year. So per year there are 365 days, and apart from that 225 days are the working days. Per day the working hours are 9 am to 5 mm. So that's why 3 plus 5 means total 8 hours are working hour per day. Maximum number of trips per hour. So maximum number of trip, that means the crane travels from the single point per hour, it's a 3 times. So for that the particular point the crane pass through 3 times per hour. So this 3 number multiply by 8 hours multiply by 225 days are the total number of repetition of loading and unloading at that particular point, which one is known as the fatigue application of the gantry girder, and the lifespan is 50 years. Means this total is multiplied with the 50. There are the total number of the cyclic loading repetition due to crane movements on the gantry girder. So the solution is maximum moment is 676.6 kN, maximum shear 377.34 kN, section modulus Z is Z as we obtained here. The gamma ft is 1.15 as per the table 25 IS 800. Actual number of stress cycle NSC is equal to 3 trips per hour, 8 hours per day, 225 days working per year, and total year 50 as a lifespan. So during its lifespan the total number of 2,70,000 cycles repetition of loading and unloading is applied throughout the gantry girder. So for that the detailed category, the gantry girder section of example 13.1 means as per the previous example corresponding to details category 59 as per the table 26b of IS 800 2007. So everyone please go through that the table number 26b and refer the detail category 59 as per our case. So the FFN value for that the category 59 is given as 59 Newton per mm square. Design normal wrench race. The equation is given just right beyond side of this particular formula. FF is equal to FFN under root 3 5 into 10 raised to 6 divided by NSC. 59 in the cubic root of 5 into 10 raised to 6 divided by 2,70,000 NSC. So your FF answer is 156.09 Newton per mm square. Assuming fail-safe and proof accessibility of detail, gamma MFT is 1.15. So design fatigue strength is 156.09 divided by 1.15. It's a 135.73 Newton per mm square. The actual stress range, minimum stress Fm is equal to 0. As per specification, load factor of 1.0 should be used for the calculation of the stress range. So the maximum moment 676.16 divided by 1.5 is equal to 450.77 kN/meter. So maximum stress F max is equal to M divided by Z is Z. So 451.06 into 10 to 6 divided by 3764.96 into 10 to 3. Your F max is 119.80 Newton per mm square, which one is less than 250 Newton per mm square. Hence, stress range is F is equal to 0 to 119.80 Newton per mm square. Since the actual stress range is 119.80 is less than the design fatigue strength 135.88. For this detail, the girder is safe. Maximum shear force is 377.34 kN at the factor load 1.5. So the maximum shear force would be 377.35 divided by 1.5 is a 251.56 kilonewton. Shear stress V divided by D into TW. So 0.8 into 251.56 into 10 to 3 divided by 600 into 7.6. It's a 44.13 Newton per mm square. So which one is greater than 27 divided by 1.15? It's a 23.478 MPa. So load factor is equal to 0.8. Hence the fatigue assessment is required to support the shear stress range. Tau F is equal to tau Fn in the fifth root of 5 into 10 to 6 divided by NSC. As per this one, tau F is obtained as 105.77 Newton per mm square. Design fatigue strength in shear is a 105.77 divided by 1.15. It's a 91.97 MPa. Which one is greater than 44.13 MPa? Hence the girder is safe in fatigue. This one is the end of design of Gantry girder. Please refer this video as just a guidance material, and please prepare for this chapter as this one as a lecture material, and the notes is already shared with you. The codal embedments as well, the other reference videos of like NPTEL and other YouTubers are shared in the Google Classroom. Please refer that, prepare for the examination well and perform well. Thank you so much, guys.